Alright, in this video we're going to see how to project the stress tensor on a particular plane. In order to get started, we're going to see how we do this first in 2 dimensions. Let's imagine a solid in 2 dimensions for which we have a stress, normal stress sigma 1, which is also a principal stress, and perpendicular to that, the other principal stress sigma 2. If we take this to the Mohr circle, this is going to look something like this: normal stress, shear stress, and here I'm going to put sigma 1 and sigma 2. Let me use colors to make it a little bit more interactive. Let's assume the value of sigma 1 is somewhere over here, and sigma 1 is going to be the principal stress and normal stress on the plane, which I'm going to call phase 1, which is this one, where sigma 1 is applied. Notice that because it is a principal stress, the shear stress is 0. Let's go with sigma 2. Let's say sigma 2, it's somewhere over here, also principal stress. That's why shear stress is equal to 0. And this is going to be this plane. All right, we know that the Mohr circle is going to be a circle that joins these 2 points, and it's going to have a center somewhere over here. Let me move a little bit to the right. It looks like it's not quite in the center. Okay, so let's say this is the center, and the radius is somewhere over here. So the circle is going to look like this, with the radius r. Okay, now the Mohr circle represents all the possible state of stresses for a plane at an angle between the planes of sigma 1 and the plane of sigma 2. For example, if I have here an angle theta, in the Mohr circle, I'm going to find that point by going an amount 2 theta. Let me delete this radius because I want this plot to be a little bit cleaner. So 2 theta, let's say that this angle is 30 degrees, then 2 theta is going to be 60 degrees. It's going to be somewhere over here. This is going to be the radius, and this is going to be 2 theta. Notice that I'm following the convention that the angle goes from the plane of sigma 1 to the plane of sigma 2. And in the Mohr circle 2, the angle goes from the value of sigma 1 to the value of sigma 2. And in the Mohr circle, this turns out this is 2 theta, because notice that in real conditions, if theta goes from 0 to 90, that means in the Mohr circle, this has to go from 0 to 180. Therefore, the real, or the angle that you have to move in the Mohr circle in order to get to the position theta in the Mohr circle is going to be 2 theta. So at this point, I'm going to find the normal stress sigma n and shear stress tau. All right, so let's see what those mean with an example. If theta is equal to 0, I could interpret that as I am slicing this solid. Let me do the base first. As if I were slicing the solid somewhere over there with theta equal to 0. If I were to slice the solid with such a plane, then in order for this solid to be in equilibrium, here I would have to apply a stress sigma n and a shear stress tau to keep it into equilibrium. Notice that in this particular case, assuming that I have the same stresses as the one I have above, sigma n is going to be equal to sigma 1 and tau is going to be equal to 0 because this plane is actually that same plane over there and is this point over here, right? If I go all the way to a theta equal to 90 degrees, then that means that I'm slicing my solid with a vertical plane. So in such case, this is going to be a case like this, where now in order to be in equilibrium with the stress sigma 2, the normal stress and the shear stress that I have to apply is going to be sigma n equal to sigma 2, and since there is no shear stress on that plane, tau is also going to be to 0. That is that point over here. And therefore, if I were to cut now the plane with an angle theta, which is not 0 or 90, then that normal stress and shear stress is going to be the normal effective stress sigma n and shear stress that I need to balance those stresses. And now sigma n is not going to be 0 and tau is not going to be 0 either. What's the value? That's what we're going to solve right now. But that's a physical interpretation. Okay, this is actually quite easy from the 2D Mohr circle. Sigma n is just going to be the projection of this point on the x-axis, and tau is going to be the projection of this point on the y-axis. And just from simple geometry, sigma n is going to be equal to the position of the center of the circle plus the radius times the cosine of 2 theta. And tau is going to be equal to the y coordinate, which is just the radius of the circle times the sine of 2 theta, where the center of the circle is sigma 1 plus sigma 2 divided by 2, and the radius is sigma 1 minus sigma 2 divided by 2. All right, so these are all the equations that you need in order to calculate normal stress and shear stress on a plane for 2 dimensions. This becomes quite important, for example, when we are looking at stresses on faults and fractures, because the ratio of sigma n, or actually of shear stress over effective normal stress, is what is going to tell you if such a block is moving or not. So let me add a plot over here. Let me now consider that I have the 2 halves of this solid, and it's been cut with a plane at this particular angle theta. Whether these 2 parts move respect to each other under the same state of stress that we are considering, whether it moves or not, it's going to depend on the ratio of shear stress over effective normal stress, and whether this one is equal or larger than the friction coefficient. We're going to see this later on, but this is something pretty important. So the decomposition of or calculation of stress on a particular plane is something that is going to be very important in geomechanics. And this is how you calculate that in 2 dimensions. Let's see how we calculate that in 3 dimensions, which is slightly more complicated. Okay, so let me make space over here. We're going to go now to the 3-dimensional case. And in the 3D case, we're going to draw a 3-dimensional coordinate system with axes 1, 2, and 3. Here I'm going to draw what is the solid already cut by a plane, and let's say that it is like this. Now this is in 3 dimensions. The blue lines join the plane which is cutting the solid which is underneath. This solid has an area on the plane which is, let me see if I can get the right way to show that. This area is the area A, and on this prism I'm going to have stresses which are applied in all directions. So for the example, we're going to calculate the summation of forces in direction number 1 and make it equal to 0. And in direction number 1, what I'm going to have are normal stress on phase 1, sigma 1, 1, applied on the face that it's behind this element, this volume. That stress, sigma 1, 1, is going to be applied on this let me delete that. Is going to apply on this area over here. Just one sec, that my shading wasn't that great. One more try. Oh. Okay. Sigma 1 is applied on the back surface, which is here on the side that we cannot see. And this one is called A1 because it is perpendicular to direction 1. Similarly, we're going to have the area on this side, which is A2, and this area of this volume, which is A3. And in direction 1, I'm also going to have here shear stress sigma 2, 1, because it's on phase 1 in direction 1, and over here on the bottom face, I'm going to have shear stress sigma 3, 1. In order to keep this volume into equilibrium, we have to do something similar to what we did in 2D conditions. To add a stress, a normal stress, and a shear stress, so that this part of the volume is in equilibrium what I removed. And in order to do that, let me come back quickly to the 2D case. I applied a normal stress and the tau and a shear stress. Well, I'm going to do exactly the same now, but since I'm in 3 dimensions, I'm going to make it a little bit more general. And now this here is going to have applied an stress, which is going to be an stress on the surface A, which is the one which is facing us, is going to be an stress T. And this is going to be a vector. This is, as we're going to see, is a combination of the normal stress and the shear stress. Okay, and now I have all the elements I need to continue writing this equation I have over here. The summation of forces is going to be the normal stress sigma 1 times the area 1 plus the shear stress sigma 2 times the area 2. Remember that all of these are stresses and therefore have to be multiplied by its areas. All of that is going to be equal to the component of T in direction 1 times the area A, the area facing us in this element. All right, so this is going to be our equation number 1. We're going to come back to this equation in a bit. In order to utilize the geometry of this volume, we're going to write the following relationships. And this is going to be our equation number 2. The volume of this particular element, I always forget the name of this geometric element, is going to be a third of the product of the base times the height. And if we take the case, for example, if we take as height the distance between the origin normal to the plane A or the area A, then this is going to be the formula, right? Let's actually draw that so it's a little bit clearer. I'm going to draw the same prism, 2, 3. Let me go down a little bit more to make space. 1. The volume here is something like this. And now the vertical line that joins the origin of the coordinate system with the plane A, that is going to have to be a normal line to the plane A, and that's what is going to give me this distance h, or the height. And let me write this over here. This distance is h. When I multiply the height times the area, I get the volume. And as I was saying before, this is going to be a normal stress. And let me actually change the color of this to just black, and I'm going to use the green color to denote that following this line normal to the plane A, I'm going to have a vector n which is normal to the surface A. All right, so n is perpendicular to the plane A. this vector n is also a vector with a length equal to 1, and it's going to have as components n1, n2, and n3. All right, let's follow with the equation that we had on the right. This equation for the volume, it is valid for any base and height that we choose. So for example, I could repeat this equation, writing it in terms of base of the area number 1. And if I do that, notice that the height that applies to that perpendicular to the area 1, which is this one here in the back, is going to be the distance between the origin of the coordinate system and this point A. So it's going to be times this length. And similarly, as I have a point A, I'm going to have also a point B and a point C. All right, so since these two volumes are the same, let's use these equations and write them next to each other. This equality is going to mean that I can get rid of those 1/3, and it allows me to write what is each area as a function of the main area, where the main area of that I'm considering is A. So A1 is going to be h divided the distance OA. And h divided the distance OA is actually going to be a cosine. And it's a little bit easier to see in the other planes, but let me write the equation first. Area A1 is going to be equal to the cosine between A, the origin, and N, where N is this point on the plane A, times A. Similarly, A2 is going to be the cosine of B ON times A, where now we can see a little bit more clearly, for example, what is BON, right? The angle BON is this angle, and the cosine is equal to the height, which is this length, divided this distance OB. And finally, the cosine of CON is going to be this. This one is a good word in French. This one is not. All right, so these are going to be our cosine directors, and actually are going to be the components of the vector n. The vector n that we have over here is just going to be composed by these cosines. And therefore, we're going to be able to write each of these areas, and I'm going to extend this to initial notation. Each area AI is going to be equal to the component Ni, where each of the components, this is going to be, let's just write it out, N1A is going to be N2A, and N3A is going to be Ni times A. This is not the nth. This is the equation that we get from our formulation for section 2. But now we can use, let me zoom out just to make it clear. Notice that in the first equation that we had A1, A2, and A3, right? But now I can write those as a function of the cosine directors and A. So let's go ahead and do that. And if I replace, let's write over here, 1 and 2, the result is going to be that sigma 1, 1 times A1 is now N1 times A. Sigma 2, 1 times A2 is now N2A. Sigma 3, 1 times A3 is now N3A. And that's equal to T1 times A. And notice that A is everywhere in each term, so I can cancel this out. And I get to a simpler expression in which, let me now just move T1 to this side. T1 is going to be equal to sigma 1, 1, and let me go ahead and write this in matrix notation. T1 is going to be equal to sigma 1, 1 times N1 plus sigma 1, 2 times N2. But since I know that sigma 2, 1 is equal to sigma 1, 2, I'm just going to put the other term over here, the symmetric term, and sigma 1, 3 times N3. And I can do exactly the same for all T's, T2 and T3. And this is what I'm going to find out. That the vector T, the stress T required to keep the solid in equilibrium for this three-dimensional cut that we did on the solid is going to be equal to the product of the stress tensor times the vector composed by the cosine directors of the vector normal to the plane that I am considering. And if I put this into vectorial notation, is the vector T is equal to the stress tensor product the vector. Let me remind you that when you do this type of product, of matrix product, you always do rows times columns. So the first element is the first row times the column. The second element is the second row times the column. The third element is the third row times the column, applying always the distributive law. Okay, so now we have found out what is the stress T required to keep this solid in equilibrium with the stresses applied on the faces. Okay, if we want to now convert this vector T into the normal and shear stress, we're going to have to do one more step. And remember that this vector T was applied, it's not necessarily normal to the area, and it's in this case somewhere over here. And this vector T, I'm going to just draw here the area. Let's see if I can do this without the axis. This is the volume that we are looking at, and on the face which is facing us, apply somewhere over here, I have the vector t, and that vector t can decompose on a normal direction. And let me give t a little bit more inclination, actually, as how it is in the previous plots. So if this is t, then t can decompose into a normal component, sigma n, which is going to be a vector if I give it a direction. And on the plane, I'm going to have another component, which is going to be tau. So let's assume that this component, when you get to do these 3D plots, it always gets a little bit more difficult. So let's say that tau on the plane is this. The important thing here to consider is that t is the vectorial summation of sigma n, which is perpendicular to the plane A, plus the shear stress T. So if we want to calculate, for example, sigma n, what we're going to have to do here is to multiply T times the vector normal to the plane. The value of sigma n, the magnitude of sigma n, is going to be equal to the dot product between T and direction n. The dot product of two vectors is going to give you just one value, a real value, right? And physically, this means a projection of sigma n on direction n. And tau is going to be equal to the magnitude of tau, the square root of the magnitude of t squared minus sigma n squared. And this equation comes from the Pythagoras rule and the vectorial summation, in which the magnitude of t squared is equal to the magnitude of sigma n squared plus tau squared. So just by moving tau to the left hand side is how we obtain the value of sigma n and tau. All right, so we know now what is the value of sigma n and what is the value of tau for 3 dimensions. And we know also the direction of sigma n, because we know that it's aligned with the direction normal to the plane that I am interested in. So this is what you're going to have to do in 3 dimensions. But if we want to get a little bit more into real applications, we have to agree on a coordinate system that we're going to work with. And since we're going to work in these applications of geomechanics and geophysics, in which usually we relate our measurements to a coordinate system, and we orient, for example, faults with respect to east, to north, to a horizontal plane, then we're going to use that in order to calculate what is the direction also of the shear stress. All right, so in order to do that, we're going to have to use some conventions. The math is exactly the same, but we just need to do a few more things here in order to get to our final equations that we're going to use in practice. Okay. What we're going to use is what is called the geographical coordinate system. This is going to be the common ground in which we write our principal stresses in any place and also our fault and fracture direction. In this geographical coordinate system, we're going to have as the first element of the base the north, the second element the east, and the third element to be depth. And if we follow the right hand rule for the coordinate system, this is going to look something like this. Let's say that the north is going inwards into the page, the east is going along the page to the right. If this is the case, the third element D is going to be going down. This is going to be depth. And this is the coordinate system that we're going to use in order to write any state of stress, whether it coincides or not with the principal stresses with the vertical direction. So let's assume that we have some coordinate system or some principal stress or some state of stress for which these are the principal stresses and these are the principal directions, 1, 2, and 3, then I could write this vector into the geographical coordinate system if I follow a couple of rules. Okay, so let's see how that works. These are the principal stresses and directions, and under such conditions I can write the vector, the tensor, the stress tensor as SP with the first element on the top, intermediate stress in the middle, and least principal stress on the bottom right. This is the convention whenever I'm writing the stress tensor in the coordinate system of the principal directions. I can write this stress tensor in the coordinate system or in the geographical coordinate system. I'm going to call it SG. And in the general case, all of these values are going to be non-zero values. And the equation that allows me to do that is the following. SG is going to be equal to a change of coordinate system matrix RPG transpose times the stress tensor with principal stresses and written in the coordinate system of principal directions times again this matrix of change of coordinate system. All right, what is RPG now? The matrix RPG is going to be a 3x3 matrix that depends on angles alpha, beta, and gamma that I'm going to describe in just a sec. But remember, what we're going to do is we're going to write the stress tensor going from the principal directions into the coordinate system utilizing northeast and direction down. All right, this matrix RPG depends on the orientation of the principal stresses with respect to the northeast and down coordinate system. And I have uh, those sketches right here. If you visit this link, then if you go to tensor method, this is what we're doing. We have a matrix and a tensor written in the coordinate system of the principal directions, and then we're going to write that in the coordinate system of the northeast and down. So the matrix is going to be this one that involves multiplication of cosines and sines of alpha, beta, and gamma, and it means the projection of one coordinate system into the other. All right? It's just geometry and projections of the elements of a base into another base, where these alpha, beta, and gamma are the angles that determine the rotation of such coordinate system. I'm not going to make your life difficult in going into cases in which all alpha, beta, and gamma are different than 0 or 90, but we're just going to see cases that apply to normal faulting, strike slip, and reverse faulting. And for those particular cases, this is a lot easier to look at. And alpha, beta, and gamma are associated with the azimuth of direction of the horizontal stresses and take either values for beta and gamma of 0 or 90. If you want to see what alpha, beta, and gamma are, I recommend that you check this animation over here. Let's see if it's working. No, I'm going to have to run it again. I'm going to have to, okay, let's just wait a bit. I know this is going to work, so let's just wait a minute. This is building, and we're going to see what is the meaning of this alpha, beta, and gamma. But at the end of the day, what I want to do is just to obtain this matrix in or tensor in the geographical coordinate system. Here you have a few examples where you can try your own equations if you write it on your own and see if they work for given orientations of the principal stresses. And for faulting regimes, you have three cases: normal faulting, strike slip, and reverse faulting. And let's see if this is done. I'm still working on that. Okay. And we want to do this because at the end of the day, we want to compare or actually to work in the same coordinate system, both for the stresses and for the fault. And we know that faults, the strike and dip of the fault, those are referred to northeast and also to the horizontal plane. So we're going to use those in order to relate those two. Okay, it's taking some time. So this is the widget from Professor Foster. And there we go. It's ready. Now let me run all of this. Yes. All right. So now you see we have here the northeast and down coordinate system, and I have the principal stresses S1, S2, and S3. So alpha if beta and gamma are equal to 0, alpha tells me what is the angle between the north and S1. This would be the case for reverse faulting because S3 is vertical. If, for example, beta is equal to, okay, I went too much. If beta is equal to 90, now we have a case of normal faulting because the maximum principal stress is vertical and S3 is horizontal, and now alpha is going to be the angle between the north and S3 and SH mean. And the last case is going to be, let me just double check over here. I don't remember those by heart. So, okay, strike slip is going to be the opposite. So, beta is going to be equal to 0, gamma is going to be equal to 90. And now the maximum principal stress is horizontal and the minimum principal stress is horizontal too. And the angle alpha tells you the angle between the north and the minimum principal stress direction, or the azimuth of SH mean. All right, so we want to do this because we're going to relate, as I was telling you before, this stress system to the system of the fault. And for the fault, we're also going to have another coordinate system, which is the system composed of the stress, of the vectors that are normal to the fault. That's going to be NN. On the direction of strike of the fault, that's going to be NS. And on the plane of the fault, and that's going to be ND or N deep. So this is normal, strike, and deep. The first element is actually deep, the second element is strike, and the third element is normal. So you can check that with the right hand rule, and you will see that if your index is pointing down in direction of the deep, your middle finger is horizontal in the direction of the strike, and your thumb is going to be pointing up, and that's going to be the vector normal to the fault. Just a reminder about what a strike is. Strike is the intersection between the fault or fracture plane and a horizontal plane. So NS is always going to be on a horizontal plane. And deep is the angle between the horizontal plane and the direction of the maximum slope on that fault or fracture. Okay, now with these vectors NN, NS, and ND, we can finally apply the math that we worked on at the beginning. The stress on such fault or fracture is just going to be equal to, if we're working in the coordinate system, on the geographical coordinate system, is going to be SG times NN. Notice that now it's NN because this is the normal vector to the fault or plane. The total normal stress, since we're using here total stresses, this is also going to be a total normal stress, is going to be the projection of T on that normal direction. And finally, here we can calculate the direction of shear stress on the direction of the dip and on the direction of the strike. And let me zoom in. These are going to be T projected on the direction of the dip and T projected on the direction of the strike. mathematically represented by a dot product. And now we have all the full components of shear and normal stress on a 3D fault or fracture for a given 3D stress tensor. One more thing that you could do here is to calculate effective stress, and in order to do that, you just have to subtract to the normal total stress the pore pressure, and that's how you obtain the effective normal stress. And also you could calculate the total value of shear stress, which is the one that we obtained before. Let me move this over here. Okay, so this tau over here is the same that we calculated before, right there. And these two equations are going to be the same. But with these new equations, we have been able to further decompose the shear stress into the direction that coincides with the dip and the direction that coincides with the strike. Now, finally, the last thing that you can do is to calculate what is called the rake. And that's going to tell you in which direction the fault is moving, up, down, to the left, to the right, or at a given angle. And that angle is going to be the arctangent of tau d over tau s. The bigger the tau d over the tau s, that's going to mean that's mostly moving in direction of the dip. If, for example, tau dip is 0, then that means, and tau s is not 0, that means that it's moving along the direction of the strike. Okay, this was a long lecture. I'm just going to do one more thing here, if OneNote allows me to do that. Okay. I need to complete in my notes the coordinate system for a fault. With the same coordinate system I used before, north, east, and down. If I had a fault which is oriented within that three-dimensional space, then here we said we define along the dip on the plane of the fault. This is ND, the first element. Second element is on the strike, and this one is NS. And the third element is going to be the vector normal to those two and normal to the plane, which is NN, where the values of NN, NS, and ND, you can find it here in the notes, and also are a combination of cosine and sines of strike and dip. Where strike is the angle between the north and the line of strike. So this is the angle of strike. The line of strike is the intersection between the plane and the horizontal plane, and the dip is the angle between a horizontal plane and that plane of maximum slope. All right, then this is it for this lecture, and using all these equations, you're going to be able to obtain the projection of normal stress and shear stress in 3 dimensions, and be able to do something similar to what I have over here, which is to calculate and plot 3D Mohr circles and calculate also normal and shear stresses within that state of stress where each dot is a particular combination of sigma n and tau. And later we're going to combine this with the stereo nets that tell you what is the orientation of the fault to further understand what that means in terms of fault or fracture reactivation. All right, now this is it.